Something's fallen off. Not too many things around here.
What did I do?
Bucket of pencils. Man. This thing go here. Okay. Oh. Oh. Yeah. I have to be careful with this stuff. It's falling off my desk. Space. Ground everything there. Let's see. So I can print this out. streaming this one. I have to do that before the class. This is really not the best way to do it. Yeah, printer is offline. Printer is online. That's what we need. That's a little introduction for the class. There's some data introduction that I need to show it on the right board. Okay. It's 3 already. It's already 3. Okay. So anybody join in here, the lecture will start at 3:30 is our class time. So I'm just gonna hang around and enjoy myself drinking coffee before 3:30. You can do the same thing. I was just checking the my video on the other computers. Of course, I get a lot of noise background. I hope you can see the board very well because that's important. Because I'm going to be writing some stuff on the board. Looks like this camera is working well. Yeah, this camera is a lot better for me than the laptop camera. Much better, much better. Much better camera. So, Rita, what fresh food do you need?
Oh, fresh food, onion, and carrots on the container.
Don't you have onions outside?
No, I already bringing it. Already done. All the produce outside is already gone. So that is.
I'm gonna have one case bucket where we're gonna put fresh food.
You
So
probably need two.
other stuff can stay outside, but fresh food I'm gonna put in the bucket. So we can select that, and then we can wash that outside. Yeah, you you have the bucket for
What about green tea?
clothes.
Downstairs.
Yeah, then bucket where we wash it outside. So we don't bring anything inside because it's not the fresh food doesn't have the spice doesn't stay long there. But
Usually, you already put it outside like the 4 days.
yeah, in the garage. But you have fresh food, you cannot put in the garage for 4 days. That's a problem. The cans can stay there for a week. Yes.
Yeah, we put everything we put outside, we 3 days.
So now it's debatable how good is this sun. No, this one is not good. It has to have UVC to get blocked by ozone, so that doesn't come down much. That would be a really good way to kill the virus, but also hurt humans and everybody else. UVB does come up as a 5% of the sun's energy, and it does a good damage to anything, and that might be disabling virus. It's not to be trusted. We need the summer sun. This is not good enough. The summer sun has a 10 times more energy than this sun. So we need that July thing to come. Yeah. July sun will be much harder on this virus. So now the Michigan got report they have 78 deaths. I'm still waiting for Massachusetts and Illinois and Washington and Texas and Connecticut and Colorado. They didn't report anything yet. They will have something. This is really very bad.
bacteria that accumulates always around the refrigerator. Those are also shoes imprints here. Used to do Clorox cleaning when I was on vacation, but since you're not going anywhere, I'm not doing anything. I always knew bleach is the thing to use. If you can stand it, because it's not very good on your lungs either. But if you can stand it, that's the thing. Chlorine kills every single alive thing that is, including humans. It was used in the First World War as a biological weapon, as a chemical weapon. It would kill a lot of people in the First World War. And the Germans used that also in the Second World War in Crimea. They would kill a lot of Russians with that. Hydrogen peroxide is much less dangerous, but it's also unstable. Chlorox is better, but it's stable. And more stable. Not that it's stable, but it's more stable. Oxidizes slower, so it works for days. Well, not for days, but surely for hours. As long as you can smell it, then you know it works. Because you can smell it, you smell the chlorine. That's what is the smell. Oh, good. So, folks, if you wanna put something in the chat over there, you will need to have a Google account, which is something you have already. If you have a Gmail, you'll be able to log in and post it. If you don't have a Google account, I think you're not going to be able to post any chat. And I might not be able to see because you can see my glasses. I'm not exactly. 2020, so I'll try to read it if I can. And also I have a little delay, like you will have probably a couple of seconds delay, so don't be surprised. It depends on your internet connection, of course. So I'm still waiting another 15 minutes. According to my clock, it's 3:18, so I have 12 minutes to go. To make sure that people show up in the beginning, I don't want to start anything because we're gonna have a topic that is not exactly simple. So we wanna have everybody in before I can start talking. It would be a good idea if you have prepared yourself to have that lecture. There are 5 pages of the lecture, to have it handy. That is a lecture number 10. It says in the lectures and practice tests. So this is the next to the last lecture that we need to do before we can go to test number 2. So then the next week we're going to be talking about the correlation, which is the lecture number 11. And today we're going to be talking about number 10. So if you have that handy, if you can print it out, you have printer handy to do that, or at least take some notes, because there are some samples there that I will not write all of the data on the board. I will just talk about that. So you might want it handy. Also, if you're already in, you can subscribe to my channel. So the next time you don't have to wait for me to tell you where the streaming video is. You're just gonna log in the channel. You will see the videos I have there. So you'll be able to start without waiting for email. Of course, I'm gonna post that as an announcement and as an email too. Yeah. The April is going to be really bad month. I don't think anybody's gonna be joking on the April 1st. Just horrendous. Drop the chair over this. A good one. Too much rolling with this one. Regular chair's gonna be better. Right.
all this dust comes from? Trying to order something from Giant, but you can't do nothing.
Yeah, it's almost, that's what they say, even if you can order online, nobody can.
Yeah, no delivery, and well, by the way, anything I want, they don't have it. So I don't know what they are selling. The CVS, all the stuff that is needed now, they don't have any of that. That's just, the store could sell lots of stuff, but they don't have anything to sell. That's amazing. $3.25. Yeah, no, this is streaming, folks. That's, you can hear everything I'm talking to my wife and around. So I'm gonna, when I post later on the streaming video, I'm gonna cut this first half an hour off. 3:26. I'm going to adjust my clock. Slightly behind. All right, now. Why is this clock needing batteries when it has the pendulum? That's go figure. The pendulum only for a decoration. Two more minutes to start. This is 3:28 now p.m. So I guess 2 minutes we will start. As you can see, I'm
having a title over there. Today's lecture is about testing variance, population variance. So this is the lecture that you have also on the Blackboard, and in the Blackboard, this is the lecture number 10. It says hypothesis testing, one population variance. Okay. One more minute to go. All right, 3:30 p.m. time for the class. All right, so we are testing, in the past we were testing the mean of the population. So there's some claims about the mean of the population, and we were also testing the proportion of the population. So this is very important when you do polling. And so that is done by z-test or a t-test. We are also testing a parameter of the population that we call variance, population variance. So population variance is a square of a population standard deviation. Its notation is just like that, sigma squared. So you need to know that. What is it? So the reason is because you have a mean of the population, and the data could go back and forth from the mean. It could go a lot, or it could go a little. So the population variance, or standard deviation, which is a radical of population variance, will tell you how much. Is it going a lot, or is it going a little? So it's important to know that. It's always important to know that, right? So this is one of those parameters that you calculate for the population. However, when you don't have the information about the population, all you can do is to do the estimate, right? So we have done this in the past. So we use the chi-squared confidence interval estimate for the population variance or population standard deviation, right? I hope you remember that we have done this some time ago. We call that the lecture number 7, right? So that can be done. But then again, also there might be claims about the variance. Somebody could make a claim about the variance. So say we have this much crime, but it's not that much from day to day. It doesn't change us that much. Well, that's a kind of claim, right? So it's a claim about the variance, not a claim about the mean, but a claim about the variance. So you can test this claim, all right? So the setup in general, when you're testing a variance, is going to be that there will be a claim about the variance. A claim is going to be just like we usually have. It's going to be H0, the hypothesis. Null hypothesis is going to say variance is equal to something. And that's something we're just going to label with a 0. So it could be some number, right? This is going to be some number. So somebody's going to say this is going to be that much, okay? And then you also have the alternative claim. Now, the alternative claim is one of the 3 things, just like we have in any other test before. So you could say, well, I disagree with that. I don't think it is that way. So in that case, you can say it's not equal to what you're claiming. All right. That's called two-tail test. Now, you might have an information from the sample. The sample tells you, well, the variance is actually bigger than that, what they are claiming. So in that case, you would use the what we call right-tail test. So you say, no, it's not that much, it's more, okay? Or you could also say, if you have an information from a sample that is less, then you would say this. So I disagree with your initial claim, and I think it's actually less, okay? So this is two-tail test, this is right-tail test, this is left-tail test. So
the bias test, which is a right tail test or a left tail test, is biased based on what you know about the sample, right? So you need to have some sample to tell you that bias. If the sample doesn't give you any bias, then you're just going to assume two-tail test. Or if you just want to play safe, you can assume two-tail test, right? And again, just like before, if the sample tells you variance is actually bigger, you're not going to be testing a left tail test because it doesn't make any sense. You don't have any information that is smaller. You have only information from a sample that tells you it's bigger. So, but one of those three. So not all three, of course, right? Just one of them is going to be alternative. So I put a semicolon here. So either this one or this one or this one. Two tail, right tail, left tail. Okay. So now we need the test value. Okay. Just like before, we are going to have the level of significance. So just like before in every other test we had before, the level of significance, what is that? That is the maximum probability you're going to allow to make a type 1 error, which is the rejection of the correct initial claim. Okay, that's a big problem if you do that. So if you reject initial claim that is actually correct, you're actually doing a big error, right? This is a knucklehead error, right? So you don't want to do that. So level of significance is the maximum value you're going to put on the probability that could happen, right? So you're going to usually use 10% or 5% or something smaller, okay? But the question is, what is the test value, right? The test value in this case is going to be based on what we know about the this variable. Okay, what is that? Well, that's a sample variance, right? So the sample variance depends on a sample. You have one sample, it's one thing. Another sample is another thing. Another sample is another thing. Another sample is another thing, and blah blah blah. You have lots of different sample variances. The population variance is only one. There's only one population, but the sample variance could be lots of different things. Okay, so what do we know about this guy as a variable? This is what we know. We know from this is the stuff we had before. If you multiply the variable with the degrees of freedom, and then you divide that with the population variance, you will have what we call chi-square random variable. So this guy is a chi-square random variable. Well, that will happen only if the population is normal. So which means the whole story we have today is only for the cases when the population is normal. Okay? So the population must be normal. If the population is normal, then this guy will be a chi-square random variable. Now, the chi-square random variable is asymmetric, which means that basically the distribution looks like something like this. Okay? It's an asymmetric distribution. And by the way, it's always positive. So it's only on the positive side of the variable axis. Well, that's obvious, right? Because then -1 is positive. This is a square. It's positive. The standard deviation is always positive. And this is also positive. So this could only be positive. Okay. Now the question is, where is it? This guy, a variable, is going to be here most often. You can see the hump, right? Most often here. But it could also end up here. It could also end up here. So those are the tails. So the same story as before. The critical rejection criteria is when this guy is in the tails. Okay? In the tails, if you have two tails, test, or in the right tail or in the left tail, depending what bias test you have. If you have a right tail test, then it's going to be in the right tail. Left, or you're expecting it to be the right tail, or if you have a left tail, it's going to be in the left tail. So if it happens to be in the tail, then you're going to have rejection. You're going to reject this guy. Okay? So I'm talking about the tails here, right? So this could be the value in the tail, and this is for two tail. But if you have a left tail, only this one. If you have right tail, only this one. And that's going to be what you want to have, no more than level of significance. Okay, so you're gonna, first of all, you're gonna have a problem of finding where are those tails. So let's say our first example in the lecture, if you look at the first example in the lecture, says, I want to find out the 10% right tail when I have a chi-square distribution that has 8 degrees of freedom. Okay, that's the example number one. Right? So I'm just talking about distribution. I don't have any particular test. I just want to find out if I need to find out the right tail, so that this would be 0.1, as in 10%. So the area is 10%. I need to know what is this value here. Okay, that is what we call a critical value. Critical value. So I want to know where this tail starts. Okay, what is the value here, so that you can say once you pass this value, you're in this 10% tail. And of course, again, this is distribution with 8 degrees of freedom. Okay, now you need to have your chi-square tables. Okay, so you can find that. I don't have a chi-square tables here, but I know where it is. We have a handout, or you have a textbook, or whatever you have, and the in that handout, on the bottom is handout, says chi-square tables. All right, in the chi-square tables, you have a degrees of freedom on the left side, on the left margin, and we are looking for 8 degrees of freedom. So we are looking for 8 degrees of freedom. Okay, and on the top you have this alpha, and we have done this in the past, so this is not unused to you. This is actually the right tail. So you're looking for 10%. 10% for the alpha. And I'm reading my tables. I have that on a computer. It says the number you're looking for is 13.362. So the critical value is approximately 13.362. So this is how you're going to find this. All right? So if you need to find out the critical value for the tail, of course, you need to know what the tails you're looking for. You're looking for a 10% right tail. Then you're going to look for the 8 degrees of freedom. You're going to look for that alpha. In that alpha, you would have 10% on the top. And on the side, you have 8 degrees of freedom. And in that crosshair, so you have 8 degrees of freedom, 10%. You will find number 13.362. So again, I hope you have those chi-square tables. I can't show you everything here, but the number I found there is 13.362. What will happen if you need a left tail? Okay, let's say you need a left tail, because you might be doing left tail test, right? Then you need the 10% left tail. So this is like, I'm trying to make a sketch. This is like a 10% here, right? So which means that this piece here is 90%. So now you need this critical value. So if you're doing a left tail test with a 10% significance, you will need 10% left tail. Okay? So you need, what is this number? Because you're looking for when the test value is going to be somewhere here. So you need to know the test value is actually smaller than this number. So you need to know what this number is. Okay. So you can again go to the table. This time you're looking for the right tail of 90%. So look at the top of the table. It says 90%. And again, I'm looking for the 8 degrees of freedom. I found the number to be 3.490. Okay. So in the 8 degrees of freedom chi-square distribution, the left tail of 10% happens before 3.490. That's it. Now you know everything about this tail, so you can say, once you calculate this guy, you can say whether it's in the tail or not. Okay, so this is very important. Okay, to be able to find the tail, of course. Right? If you don't know what you're looking for, you're doing the test, you're calculating some numbers, you have no idea what they are. Right? Okay, so let's do some actual test here. So I have this example number 2 in the lecture. You have an example number 2. I'm going to read it for you. I do have the data, but of course the data is in the lecture, so you can find it yourself. The story in the whole example is about the so that is in the you're going to find this in the lecture, the example number 2. So you can see the numbers over there. Okay, I'm going to just tell you what the numbers are. I'm not going to write it on the board. There's just too many of them. Okay, what we have here in this example is that we are talking about a Holstein cow. Holstein cow is a cow that produces a lot of milk. So those cows are used in the industry that is making milk and selling milk to you. Still important nutrition for many people. Okay, now these cows do have they're giving a birth to a small one, to a calf, and after they're giving the birth, they're actually producing a lot of milk. And of course, it makes perfect sense, right? Because they need to feed the calf. Okay, so while they are producing a lot of milk, that milk has a tremendous amount of fat, as you probably know. So the milk has a lot of fat, and well, not tremendous, but a lot of fat. It's surely less than peanut butter, but it still has a lot of fat. And so we are actually examining how much is this cow producing butter fat in a period of 305 days after the giving a birth of calf. Okay, so the first cow in my sample makes 425 pounds of butter fat. Okay, that's how butter is made, right? In 305-day period, so you get more than 1 pound of fat per day. Okay, the second cow has 710 pounds of fat. The third cow 661, and in this sample you're going to find a cow that has a 934 pounds of fat. You will also find a cow that has only 405 pounds of fat. So you can see it's a big difference from cow to cow. Some of them are having a lot of production of fat, some of them having much less. Okay, so there is a significant variation. This is what the variance is about. So the population variance, we don't know what that is, but somebody has claimed that the population variance is 140 square. So which means, now you can square this number. I don't know what that is. If you square 140, I'm just keeping it as a square. I'm going to square it so I can tell you what it is. But that's a big variance. Yeah, looks like I need to change my batteries. I'm having large numbers, like a 19,600, okay, square pounds, okay? It's in square units. The variance is in square units. Okay, so that's a lot of variance. But, so they claim that the variance is 140 square. Again, this is like a 19,600. That's the claim. Now, when we look at our sample, in our sample, in our sample, you can calculate standard deviation. So this is the example number 2 in the lecture that is on the blackboard. So all of those numbers there, I have the 25 cows. So that's going to be 24 degrees of freedom. But 25 cows, I calculate that sample standard deviation is 154.3615669. So I calculate this guy, and out of the sample. Of course, you're going to use a calculator for that, right? You're not going to be doing that on table. But you can certainly use a table if you like. Obviously, I didn't. I used the calculator. 154, and I have a bunch of decimals there. 3615669. Okay? So that's the sample variance squared, right? The 154.3615669 is the standard deviation of the sample. That is bigger than 140. So this number is bigger than 140. So I'm inclined to believe that this is not true. And I'm inclined to believe that this is more. So I think that in this case, we're going to use the right tail test. So we're going to claim that the variation is bigger than what was claimed in the null hypothesis. So we have alternative hypothesis. If we reject the null hypothesis, we accept the alternative hypothesis, and vice versa. So I think it's more. I do have some evidence that it's more, but it might not be. We'll find out, right? Okay. The next thing I need to do is to calculate this guy. This is my test value, so I need to calculate that. Again, n minus 1 is 24, because the sample is of 25 cows. So you subtract 1, you get 24 degrees of freedom. Now, this s squared is that number over there, so I can do that. Now, the only question is, what is this number here? This is a population variance, which I don't know, right? I don't know what a population variance is. But we will assume that this is true. So we are assuming if we're going to hang this by its own rope. So we're going to assume this is true. So we're going to use here the zero value, the one that is from the null hypothesis, from zero hypothesis, right? So null value is 140 squared. Okay? This guy here is 154.36 and a few more decimals. I'm not going to write them all down. And this guy here is 25, so I get 24 here. I have to multiply. Okay. So the business you're going to do is your calculator here. So it's not something difficult for you to do. You're going to multiply this guy. Oh, I forgot to square here. This is very important. Okay, you cannot forget square, because if you forgot square, everything's going to be completely wrong, right? Okay, so you have 24 degrees of freedom, sample variance, population variance assumed, and I got the value, not the calculation, 29.1765. Obviously, this is approximation, right? A pretty good approximation, because lots of decimals. I use the calculation with lots of decimals. Okay. So the question is, are we on the tail or not? Okay. What level of significance we're going to use? Now, so if you don't have any better idea, if you're not looking for something really, really, really careful, or something really, really relaxed, we usually use 5%. So we are now looking for 5% right tail. Okay? I need to find this number here, and I want this to be 0.05, 5%. I need a critical value. And once I find the critical value, I will know whether this number is past that critical value. If it's past the critical value, it will be in the tail, and then we will have rejection of the null hypothesis. So my next step is to look at the table, to find chi-square critical value when the distribution, the chi-square distribution is with 24 degrees of freedom, and I want to have right tail of 5%. Again, you need to open the tables, and in the tables you can see that on the second page of the table is 24 degrees of freedom, and I'm looking at the number of alpha to be 5%. So the critical value that I'm finding in the table is 36.415. And again, this is also approximation, but it's pretty good approximation because the 3 decimals there. So so what do we know now? Well, we know that our value, the test value, is not in the tail here. Our test value is actually before the tail, somewhere here, right? So what does that mean? That means that we cannot reject this guy. We do not, at the level of significance of 5%, we do not have enough evidence to reject the original claim. So the original claim stays. I mean, we are not accepting, we are not saying that this is true, because we have an indication it isn't. But with the data we have, with 25 cows we have in our sample, we do not have enough evidence to claim it isn't this. So this is one of those tests when you conclude the test and you have no reason to reject the original claim. And again, it's never about acceptance about this guy. It's always about acceptance of this guy. You cannot accept this guy because you just didn't reject this guy. So that's the test. Okay. Let me go on the second example. Now, this second example could be really important right now in the situation we have with this healthcare emergency in the country, this pandemic that we have, right? What is the second example about? Well, the second example is about emergency response time. Okay? What do we want from emergency response time? Well, we want it to be as small as possible. So when the house is burning, you need a fire truck as soon as possible, in minutes. You don't need it 2 hours after. Okay? That's one of the problems. But that's about the mean. But we also don't want to have that on one place goes in 4 minutes, on another place goes in 50 minutes. We don't want that either. So that is a huge variation, right? So if you have a huge variation in emergency response time, for example, for fire department, that means you're not well organized, which means that the network of fire department is not placed properly. Because in one place you're sending the trucks really fast, in another place you take a long time to go. So that is not a good organization, right? So that's a problem. So the problem is how fast you are, but the problem is also that you don't want that to be on one place really fast and another place really long. So the variation of the emergency response time is very important, and it has to be as small as possible so that you have equal response on every emergency that you have, right? Because the taxpayers are paying equally. So if you are funding your emergency response, it better be equal to everybody. And it won't be 100% equal. Of course, we know that because nothing can be made perfect, but you want to have it lower. Okay, so in this example, we have a variance of emergency response time in minutes for fire departments statewide. And it's claimed to be 18.6, which means that the claim was that emergency response time variance of emergency response time is 18.6. I'm not squaring this because in the example says this is variance, right?
doesn't say this is a standard deviation. Standard deviation is 4 point something, radical of 18.6, if you want to find that out. So this is the variance, right? You have to be careful about it, right? When the statement says variance is this much, that means that's a variance. If the statement says standard deviation is something, then the variance is going to be square root. Okay? But this says the variance is 18.6. So we have 18.6. Okay, so now what they were doing reorganization. So they wanted to reorganize this because they thought the variance of 18.6 is kind of like too much. Okay, so after that reorganization, they are sampling, so to see whether they have any better now. So after that, they have the sample of 16 emergency. They find out that in that sample, the standard deviation of the sample is now lower. It's 9.3. 9.3 square minutes. What do you see here? It's half of this. So you could, if you're a politician, you will say immediately, oh, we have organized this nicely. Now we have much better organization. We halve the variance, the variation that we had before about emergency response. Now we halve that into half of what was before. Now, the question is this really true? Okay, what's the story about? Well, population variance, sample variance, those things are not the same. Okay, this is based on the sample of 16. Is that enough to say that this thing here, this is population variance, really went down? I don't know. The sample variance went down. Okay, in the sample of 16 emergency, it seems to be that the variance went down. Okay, but now we have to make sure that that really is something that we can claim, right? We're not politicians, we are scientists. So this is a quantitative analysis. A quantitative analysis ought to be precise, ought to be based on facts. You can't just go on and claim the things you feel to claim, right? That is what politicians do. So what we have here is an indication that variance went down. So it's not anymore 18.6, is lower than 18.6. Okay? In other words, alternative here that we would like to accept. So we would like to accept this claim. We can accept this claim only if we reject this claim. So we are looking for rejection of this claim. There'll be acceptance of this claim, and then we can say, like politicians would say immediately, that variation went down. Okay? But only if we can accept this claim, which means rejection of the H0. All right. So the next step is to calculate the test value. And I said it in the class many times. This is often called test value. It's also often called test statistic. Either way. Okay. So now you have, and this again, we're going to use the one here. So we will accept this as true while we are testing. And then if it isn't true, we'll hang it by its own rope, right? So we're accepting this as true. So now you have this n-1. We have 16 emergency. So this is 15 degrees of freedom. S squared is 9.3. And this guy here is 18.6. Notice, I'm not squaring anything because I already have the variances, right? So you have to have a good ear here to pay attention that when you have an example or a problem and it was given to you standard deviation, you will need to square it. If it's a variance that is given, you don't need to square it because it's already a squared, right? So this is really easy to calculate. It's not much of a calculation. It's 7.5 exactly. Right? This is 1/2 and time 15, 1/2 of 15 is 7.5. So you get 7.5. Okay. 7.5 is the test value. The next question is it in the tail? All right. So now you have this
little sketch, you always have to do the sketch, because if you don't do the sketch, you won't know what you're doing. And sometimes people find the correct numbers and calculation is correct and everything, but then the conclusion is just ridiculously foolish, right? You don't want that, right? Because then you say, oh, I'm calculating everything, but I have no clue what I'm doing. You don't want that. So what we are looking for here is the left tail. The left tail, because we have a left tail test. And now it depends what level of significance we're going to use. So I'm using here, I wrote that in the lecture 10%. So I want this to be 10%, which is 0.1, right? So my left tail has to be 10%. The question is, what is the value here? Okay, that's the critical value. So the only conclusion you can make if you can compare the test value with the critical value. Well, you will know. If the test value is less than critical value, then it's in the tail. If it's more, then it's not in the tail. Okay, but now you're looking for the tables. In the tables, this thing here is 90%, right? That is in the table. I said it many times before. I'm going to repeat this again. When you look at the chi-square tables, the alpha that in the table, the tables is not the level of significance. That what you see in the table is a right tail. Okay. Now, if you have a right tail test, that is a level of significance. But if you have a left tail test, that's exactly the opposite. If you have a two tail test, that is going to be, you know, what you have in the right tail, and you need probably in two tail tests you need two tails. So you need two critical value. One is going to be here, one is going to be somewhere there. If you have a two tail test, then you have to be careful. But in this particular case, I am looking for 90% here, and I'm also looking for 15 degrees of freedom because I have 16 emergencies. So again, you look at the chi-square table, and you look at the 15 degrees of freedom. That is in the table. Again, I said it in the class, if you don't have that value in the table, you look for the closest one. But I do have 15 degrees of freedom. 15 degrees of freedom and 90%. 90%. My tables, chi-square tables, I have 15 degrees of freedom, 90% of the top of the table, I have 8.547. I found this number, and that's the critical value. Okay? So now what we have here is a test value. Where is the test value? The test value is in the tail, here. It's before 8.547, so it's in the tail. What does that mean? Well, that's a rejection criterion. You just met the rejection criterion. A rejection criterion is about rejecting H0. We are rejecting H0. When we are rejecting H0, we are accepting H1. Accepting H1 means that now we can say, yes, these guys have improved emergency response time, not to make it smaller, but to make it less variable. So they decrease the variation of emergency response time. So they could have done that job without spending more money, right? If you want to decrease emergency response time, you have to just make more fire departments. But to decrease the variation of emergency response time, for that you just need to reorganize what you have, right? Instead of having the 2 fire departments in Nassau County, so they will take 2 hours until they get to Hamptons, you might have one in the Hamptons, one in Nassau County. So you have the same resources,
but better organized. Right? My example is totally bunk because, of course, we have more fire department than that, but that's the kind of things you can do. So you have the same resources, the same amount of money you're spending, but you have better organization. So yes, we have that. They are, whatever they did after they reorganized the emergency response time, now they have it less. Then variation is less, variance is less than what it was before. Okay, so that's the conclusion here. This test is conclusive, right? Now, another thing I wanted to point it out is that, of course, we can talk about a p-value here. Now, p-value would be the value that is from this point on lower, okay? So the p-value, we always compare the p-value being less than a level of significance. Whenever the p-value is less than a level of significance, you also say, okay, we have a rejection. If it isn't, then we don't have a rejection. This is like the story we had before. So the p-value that I have here is 5.8%. In the lecture, you'll find it in the lecture, it's 5.8%. So 5.8% is less than 10%, which is level of significance, we assume, right? So we will have the same conclusion. But if we have a level of significance 5%, we would not be able to do that, because the p-value of 5.7, 5.8 would not be less than level of significance. Okay, now you can say, okay, Prof, can you show me how do I do that on my calculator? And my answer to that is, sorry, but that is not on your calculator. So TI-83, TI-84, by default, don't have the feature of calculating p-value for the chi-square distribution testing of one variance. You will find some chi-square tests there, but not this one, okay? And those tests that are chi-square tests you're going to find on your calculator, we're going to use down the road. We're going to have them, okay? We have 2 more chi-square tests to go after we have our class test number 2. We will talk about it. They are on the calculator, but this one is not, okay? Now, you could download the extra software, install it on your calculator, but for that, of course, you need to have the cables on your calculator. You need to register with the Texas Instrument and blah, 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 what that goes with them. And then you will be able to download some program. You need to install that program and and it's just a waste of time, okay? And by the way, whenever I have a calculator, and I almost every time I lost manual and I don't know the registration number or anything like that, so I just don't have it. So you probably are in the same boat. Of course, if you bought a used calculator, you won't have anything, right? You just have a calculator. So it's not there. Sorry. So you will have to do this by the table, which means the next time we have a test number 2, you're going to have a table handy. Chi-square tables going to be absolutely necessary for this kind of testing, because you're not going to be able to calculate the p-values. P-values are only possible to calculate with the calculator there. Or, of course, you can do it with calculus, but of course, we're not requiring you to know any calculus here. So, right? The calculus is an alternative. I said that all of those calculations can be done in the calculus. If you study calculus, that's the business there, and you can learn that by doing calculus. But we don't do that. You either use calculators or tables. In this particular case, you don't have a calculator option. You only have a table option, okay? So this is my story for today. I want you to make sure you're doing this homework on time while you're fresh. Your mind is still wrapped around this lecture, and so you probably have a better idea. This lecture will be on for a while on YouTube, but YouTube erases streams after a while. So I'm not guaranteeing it's going to be 24 hours from now, okay? They do erase streams. Sometimes they keep them for long, but sometimes they erase them. So the streams get erased. So I want you to wrap up your mind around this lecture. You have it written in the written format on the blackboard. So even if you lose the video, you're going to have it there. And I want you to do the homeworks while you're fresh, so you get this idea. In the homework, I think you have a seven or eight question. I forgot. So you're gonna get, instead of my 3 examples, you're gonna get another 7 or 8 examples, and you're gonna have to think yourself. So it's gonna be a lot more work for you. And of course, whenever you learn yourself, it's always better, right? It's teach somebody to fish or give him a fish, right? So I'm giving you fish here, and I'm asking you to go and teach yourself fishing by doing the homework, right? That's my story for today. I am done. So the next time we meet, we will be doing the next week, 2 classes next week. We'll be doing the story about correlation. So we are out of testing for a while. We'll be testing more down the road. But for a while, we're out of testing. We're going to start the story about correlation. All right? So I'll see you on my office hours. I have office hours after this. I'm not sure I have it after this class. Well, whatever I have an office hours, I'm on Skype. So you can see me there if you need to talk to me. I am done. I'll see you.